There are multiple ways of drawing organic molecules. Up till now, we have mostly drawn things that look like Lewis structures. These are sometimes referred to as extended or expanded structures. Today we're going to look at condensed structures and also bond line structures, or as it says down here, skeletal line structures. Klein actually uses bond line instead of skeletal line, but you'll see both. So let's look at the condensed structures first. The way that you draw the condensed structures is all on one line. And this was a really popular way of drawing structures before there were nice drawing programs on the computers. This was great for a typewriter. So we don't often use fully condensed structures of molecules. Oftentimes we'll use them combined with the line bond structure, or the bond line, pardon me. So if we look at the Lewis structure on the top here, you can see that in red on the left hand there's a CH3 group, and there's a carbon bonded to 3 hydrogens. It's a methyl group, CH3. And so we draw it on one line as CH3. And so we're showing all of the atoms, but not the bonds. Same thing, next store, we have CH2 group, another CH2 group in black, down here CH2. And then in red, carbon bonded to 3 hydrogens, another methyl group, and that's a CH3. So just take a moment, you might want to pause and see if you can write the condensed structure, condensed formula for hexane, which is shown here on the right. Alrighty, so hopefully you were able to translate the CH3s and CH2s into a single line, that condensed formula. Since we're just writing a bunch of CH2s in a row, one thing that you can do to shorten the amount of time and the amount of writing that you do is use a little subscript after parentheses saying that you have 4 CH2 groups in a row. So not all molecules are linear. Some of them have branches. Actually, a lot of them have branches. And so we will put the branches in parentheses all on the same line with the rest of the condensed formula. So we have a CH3, CH3, CH, CH. Now this is also bonded to a CH3, so that's in parentheses next door, and then the CH2 group and CH3 group. And so you can see those down at the bottom. Again, see if you can take a moment to pause the video and see if you can do the analogous structure over here on the right. And I see that the hydrogen up here at the top is a little bit cut off. So just note there is a CH3 group that's at the end over here, or at the top, I should say. All right, so were you able to come up with something like this? And it's possible that you had in parentheses CH3 and then a little 2 after it, and that's fine. There are varieties like that. You could have had CH3 over here on the end and then a little 2 on the end instead of writing both CH3 groups. That's also perfectly valid. So there's definitely more than one right answer here, and if any of that kind of gives you trouble, that would be a great thing to ask about for today's question. So the most common type of structure that we use in organic chemistry is the skeletal line structure, or the bond line structure, which is what Klein calls it. And so in that you don't actually show or write down all of the atoms. Nonetheless, as an educated organic chemistry person, you should be able to kind of mentally put all of those in. And so what we do is we say there's a CH3 at the end. That's over here. This is a CH2 group, CH2 group, CH2 group, CH2, and then a CH3. And so you can kind of see there's some lines there showing you how those line up. With branch structures, You can see here's kind of a molecular model, 3D model, and the backbone, this for the butane here, is shown in red. And then there's 2 branch points, one over here on that second carbon and one on the third carbon. And so those are in blue, and you can see those drawn on the bond line structure to the right. So let's see if I can find this. Your text actually has a really nice discussion of some things to remember with bond line structures. I think this is like page 57, yeah. So zigzag, the idea is to draw these bonds as a zigzag. They should be as far apart, like the one side over here, one side over here. You don't kind of want to scrunch them up together or anything like that. Just a nice little zigzag as is shown there. One thing that students will often do, and this is this little watch out down here, is to try to kind of combine the different ways of drawing Lewis structures with the skeletal or bond line structures, and try to avoid doing that. So students will sometimes just write C, 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 C with the bonds between it. That is not a bond line structure. That is nothing. So you got to choose the Lewis structure, choose the condensed structure, or choose the line bond structure, and then just stick with it. Don't try to combine those different types of ways of drawing, because you might end up with nothing in the end. All right, so down here, number 2, we went, when we have a double bond, remember that the angle should be 120 degrees. This is trigonal planar. This is not a trigonal planar structure on the right, so that wouldn't be correct. You know, it's not shown as a zigzag over here in number 3, but the structure on the right isn't really a zigzag. Nonetheless, this still represents the same molecule. And this becomes a lot easier when we start naming. These two will have the same name, and so you know that they're the same. Sometimes it's a little hard to visualize which molecules are isomers and which molecules are the same or identical. And then down here, you do need to have, whenever you have a heteroatom, and remember that heteroatoms are just non-carbon or hydrogen atoms, so like an oxygen or nitrogen, then you're going to have, and if that's bonded to any hydrogens, you need to actually draw those hydrogens in. All right. So going back here, I guess that will work. Sorry, it's taken a couple seconds, maybe longer. So you're asked to do this problem today for your prep problem. And one of the ways to approach this is to go ahead and actually add in the hydrogens. So up here I have there's a carbon right here. And this carbon is bonded to it's a double bond, so that's 2 bonds, and then 3 bonds, and then 4 bonds. So that carbon doesn't have any hydrogens bonded to it because it's already bonded to 4 things. But down here, there's another carbon, and this carbon is bonded in that double bond, so that's 1, 2, and then to the other carbon, that's 3. So that's only 3 bonds to carbon, so there's not a formal charge on here or anything, so there must be another bond to hydrogen. So you can go through the same process over here for this carbon up at the top and this one at the bottom, and then that should allow you to be able to answer this question.